Okay, let's dive right into this explainer. If you're a software developer, or honestly just anyone who's ever used AI to write code, you already know the absolute magic of watching complex logic just materialize on your screen. But you also definitely know the massive, hair-pulling frustration of the black box breakdown. You ask a large language model to write a function, it starts off brilliantly, and then suddenly, halfway through, it just completely loses the plot. It generates syntax that makes absolutely no sense, hallucinates variables, and leaves you staring at your monitor wondering if you should just throw your keyboard out the window. Well, today, we're looking at some fascinating AI news and a brand new tool designed to shine a massive spotlight directly into that black box. It's called TokenScope, and it is kind of gonna completely change how we think about AI code generation.
Here's a quick roadmap for this explainer. First, we'll look at the code generation black box. Next, introducing TokenScope. Then, real-time structural analysis, followed by interactive developer capabilities. And we'll wrap things up with current limitations and availability.
All right, Section 1, the code generation black box. Let's look at why current AI coding workflows feel so incredibly fragile. So, why do LLMs just suddenly fail during code generation? It's the million-dollar question, isn't it? Understanding exactly how decoder-based LLMs make token-level decisions during a coding task is honestly still a massive blind spot for researchers and practitioners alike. You see, the model doesn't think in entire paragraphs or complete functions. It thinks in tokens. And when a logical drift or a syntax failure happens, it's rarely just some random glitch at the very end of the output. The failure usually happens much earlier, buried super deep inside a sequence of decisions that we, as users, traditionally have absolutely zero visibility into. And this brings us to the core issue, which is essentially a domino effect. Code generation is intensely sensitive to early token choices. Unlike generating a poem or an email where a slightly weird word choice might just sound a bit clunky, code has incredibly rigid structural rules. A single misplaced keyword or an incorrect type annotation early in the generation window cascades into a massive structural failure. It literally tips over the first domino, and by the time the model finishes outputting the code, the entire logic block has completely collapsed. So traditional debugging right now forces us into a pretty painful reality. When an LLM fails, we rely on post-hoc insights. We inspect the final output, realize it's wrong, tweak our prompt, and rerun the model, just hoping for a better result. It's a frustrating, totally blind trial and error loop because the model is a sealed black box. TokenScope debugging, however, completely shifts our focus to the actual generation window. It captures decoding time signals and real-time metrics as the tokens are actively being produced, which allows for a highly interactive debugging process. We're moving from guessing what went wrong after the fact to literally watching it happen and understanding exactly why in real time. Which brings us to Section 2, introducing TokenScope. Let's officially meet the flashlight we've been waiting for. TokenScope is the brainchild of researchers Amir Riza Ismaili and Fatemeh Fard. They detailed this tool in a research paper submitted to Archive in April 2026, and what they've built here is an interactive interpretability tool that is specifically designed for decoder-based LLMs tackling code-oriented tasks. They recognize that existing interpretability tools usually just surface static model internals long after the fact. TokenScope is totally different because it actually exposes fine-grained uncertainty and decoding time signals right in the middle of the action. Now, the real secret sauce here is how TokenScope makes sense of the AI's internal math, and it does this through AST aggregation. AST stands for Abstract Syntax Tree. If you aren't familiar with that term, just think of an AST as the structural blueprint of your code. TokenScope takes the raw abstract token probabilities from the AI model and maps them directly onto this blueprint. So instead of just looking at isolated characters, it aggregates these metrics at the structural node level. When the model generates a variable declaration, a control flow statement, or a function signature, TokenScope tells you exactly how confident the model was about that specific structural piece of the program. It perfectly bridges the gap between the model's internal math and the actual code structure that we developers care about. Moving on to Section 3, real-time structural analysis. This is where we literally get to freeze time. TokenScope introduces this really fascinating concept called counterfactual branching. It sounds super complex, but it's basically the ultimate what-if simulator for AI generation. Counterfactual branching allows developers to systematically test generation stability right on the fly. You don't have to wait for the whole block of code to finish anymore. You can pause the generation, swap out a single token, and instantly see how that minor change alters the structural dependencies of the rest of the code. It effectively isolates the causal relationships between your prompt and the structural output. Let's break down exactly how you'd use this interactive token replacement in a real workflow. Step 1, you intercept the stream. The model is actively generating code and you pause it right at a critical juncture, like say when it's starting an error handling block. Step 2, you swap a token. Maybe you force it to use a different keyword or a totally different variable name. And step 3, you observe the uncertainty metric adjustments. You watch the model's internal confidence meters instantly recalculate. If the model suddenly hesitates or its confidence drops below a usable threshold just because you changed one single token, well, you've just identified a structural uncertainty signature. You have found exactly where the model is guessing instead of knowing. Alongside tracking those metrics, TokenScope also offers attention pattern visualization, and this is incredibly cool. When an AI generates a specific line of code, you need to know exactly why it wrote that line. Is it grounding its output in the function signatures and external documentation that you provided in the prompt? Or is it just relying on spurious random correlations from its massive training data? By visualizing the attention heads alongside the token metrics, you can physically map which parts of your input prompt are driving specific code constructs. You can actually verify, for sure, that the model is paying attention to your instructions. Okay, section 4, interactive developer capabilities. Let's summarize the practical toolkit this actually gives to software engineers. So this token-level explainability fundamentally transforms code generation from a super frustrating black box sequence into a highly analyzable diagnostic process. With TokenScope, you're actively monitoring decoding time signals to pinpoint exactly where model confidence drops, while simultaneously visualizing attention patterns to catch misaligned grounding. You can even perform counterfactual branching to test causal dependencies and aggregate it all via ASTs to correlate the model's internal confidence directly with syntactic correctness. This basically means targeted debugging of type systems, API usage, and control flows without ever having to retrain the underlying model. Now, we need to frame this correctly. TokenScope is a diagnostic layer sitting right between the model's raw logits, meaning the raw mathematical probabilities, and the final text output you see on your screen. It is sitting exactly where the tokens are born. It doesn't replace your linters, your compilers, or your automated test suites. Those tools tell you if the final code is broken. TokenScope tells you exactly why the AI broke it during the assembly process. All right, let's take a breath and head into section 5, current limitations and availability. Let's ground our expectations in reality for a minute. As incredible as TokenScope is, we gotta be totally clear about what it is and what it isn't. It is explicitly focused on decoder-based LLMs and heavily optimized for code-oriented tasks, meaning its AST features are built specifically for programming languages. And crucially, it's currently a research prototype. Because of this highly specialized nature, it is not optimized for general text generation, like writing essays, and you definitely won't find it integrated out of the box with your CI/CD pipelines, IDEs, or automated testing frameworks just yet. Plus, as of the paper's publication, it's not publicly available as a simple plug-and-play repository on GitHub either. What this means practically for developers is that if you want to use this tomorrow, you can't just run a quick install command. The paper is published open access and outlines the methodology and experimental setup perfectly, but production use currently requires manual implementation. You'd actually have to build the custom adapters to extract the decoding time signals and implement the AST aggregation logic all by yourself. If that sounds like way too much heavy lifting, you'll definitely want to monitor the archive page closely for future announcements regarding official repository releases, CLI specs, or IDE integration guides. But let's step back for a second and look at the bigger picture. TokenScope fills a massive, super specific niche in the code generation diagnostic stack, which leaves us with this final, really provocative question. Will real-time structural analysis become the new standard for debugging AI, replacing the black box forever? Because once you realize that you can literally look inside the generation window and track exactly where an AI model loses confidence or misdirects its attention, well, going back to the old method of trial and error prompting just feels incredibly primitive. The ability to intercept, swap tokens, and map raw probabilities to abstract syntax trees isn't just a neat trick. It honestly feels like the necessary evolution of software engineering in an AI-driven world. It empowers developers to stop guessing and finally start diagnosing, and that is absolutely something worth getting excited about. Thanks so much for joining me on this explainer, and keep learning.